This is Bukya Krishna, rule number 20951A2130, branch aeronautical engineering. So today I want to discuss about the Kutta-Joukowski theorem. Introduction. The Kutta-Joukowski theorem is a fundamental theorem in aerodynamics used for the calculation of lift of an airfoil and any two-dimensional body, including circular cylinder, translating in a uniform fluid at a constant speed large enough so that the flow seen in the body fixed frame is steady and separated. The theorem relates the lift generated by an airfoil to the speed of the airfoil through the fluid, the density of the fluid, and the circulation around the airfoil. The circulation is defined as the line integral around a closed loop enclosing the airfoil of the component of the velocity of the fluid tangent to the loop. It is named after Martin Kutta and Nikolai Joukowski, who first developed its key ideas in the early 20th century. Kutta-Joukowski theorem is an implicit theory, but it is a good approximation for real viscous flow in typical aerodynamic applications. So this is the theorem, which is fundamental theorem in aerodynamics, used for the calculation of lift of an aerofoil in any two-dimensional body, including circular cylinder. Kutta-Joukowski theorem relates lift to circulation much like the Magnus effect relates side force called Magnus force to rotation. However, the circulation here is not induced by rotation of the airfoil. The fluid flow in the presence of the airfoil can be considered to be the superposition of a translation flow and a rotating flow. The rotating flow is induced by the effects of camber, angle of attack, and the sharp tailing edge of the airfoil. It should not be confused with a vortex like a tornado encircling the airfoil at a large distance from the airfoil. The rotating flow may be regarded as induced by a line vortex with the rotating line perpendicular to the two-dimensional plane. In the derivation of the Kutta-Joukowski theorem, the airfoil is usually mapped onto a circular cylinder. In many textbooks, the theorem is proved for a circular cylinder and the Joukowski airfoil, but it holds true for general airfoils. So this theorem relates to the lift of circulation. It is equal to is much like to the Magnus effect. So here the circulation is not induced by rotation of the airfoil. It is the fluid flow in the presence of airfoil can consider to be superposition of the translational flow and a rotating flow. Lift force formula. The theorem applies to two-dimensional flow and around a fixed airfoil or any shape of infinite span. The lift per unit span of the airfoil is given by P, where given by L equal rho infinity V infinity tau, where P and V are the density and velocity. Around a closed counter enclosing the airfoil and followed in the negative clockwise direction, as explained below. This path must be in a region of potential flow and not in the boundary layer of the cylinder. As explained below, this path must be in a region of potential flow and not in the boundary layer of the cylinder. That is tau equal to integral of C V into ds equal to integral of C V cos theta ds. The integral around the closed counter C enclosing the airfoil and the followed in the negative clockwise direction as explained below. This path must be in a region of potential flow and not in the boundary layer of the cylinder. The integral V cos theta is a component of the local fluid velocity in the direction of tangent to the curve C, and ds is an infinitesimal length of the curve C. Above equation is the form of Kutta-Joukowski theorem. The force per unit length acting on the right cylinder of any cross section whatsoever is equal to rho infinity V infinity tau and the perpendicular to the direction of V infinity. Circulation and the Kutta condition. A lift producing airfoil either has camber or operates at a positive angle of attack. The angle between the chord line and the fluid flow far upstream of the airfoil. Moreover, the airfoil must have a sharp trailing edge. Any real fluid is viscous, which implies that the fluid velocity vanishes on the airfoil and showed that for large Reynolds number defined as Re equal rho V infinity Ca by mu and small angle of attack. The flow around a thin airfoil is composed of a narrow viscous region called the boundary layer near the body and an invisible flow region outside. In applying the Kutta-Joukowski theorem, the loop must be chosen outside this boundary layer. For example, the circulation calculated using the loop corresponding to the surface of the airfoil would be 0 for a viscous fluid. The sharp trailing edge requirement corresponds physically to a flow in which the fluid moving along the lower and upper surfaces of the airfoil meets smoothly with no fluid moving around the trailing edge of the airfoil. This is known as the Kutta condition. Kutta and Joukowsky showed that for computing the pressure and lift of a thin airfoil for flow at large Reynolds number and the small angle of attack, the flow can be assumed invisible in the entire region outside the airfoil provided the Kutta condition is imposed. This is known as the potential flow theory and works remarkably well in practice. Conclusion: Kutta-Joukowsky theorem is an invented theory, but it is a good approximation for real viscous fluid flow in typically aerodynamic applications. Kutta-Joukowsky theorem relates lift to circulation, much like the magnet's effect relates side force, called Magnus force to rotation. Thank you.